High in the arid hills of southeastern Turkey, there lies a mound known to the locals as Potbelly Hill. For generations, it was seen as little more than a natural rise, an unassuming bump in a vast and windswept landscape. On a clear day, one can stand atop it and see far across the plains, where irrigated farms now stretch toward the distant horizon. The hill had long been considered sacred by the Kurdish communities who lived nearby. But in the eyes of science, it was simply a hill, ordinary, unimportant, until someone looked deeper. In the mid-20th century, archaeologists began to take notice. There were stones here, carved, arranged, buried, but nothing seemed remarkable at the time. Many assumed they were grave markers left behind by some forgotten culture, and so they moved on. That might have been the end of the story, if not for a German archaeologist named Klaus Schmidt. In 1994, he visited the site after hearing local farmers speak of strange stones poking from the ground. What he found would force the world to rethink the foundations of history. As Schmidt began excavating, it quickly became clear that the site was no ordinary village. Rising from the earth were massive stone pillars, some in the shape of a capital T, arranged in circles and paths, like the bones of an ancient cathedral. These megaliths stood over 16 feet tall and weighed several tons. Many were carved with images, animals, abstract symbols, and shapes with no known meaning. It was not just the scale of the structure that stunned archaeologists. It was the age. Through careful analysis and carbon dating of organic remains found near the base of the stones, researchers determined that the site had been built over 10,000 years ago. That is several millennia before the pyramids of Egypt, thousands of years before Stonehenge, before pottery, before the invention of writing, before the wheel. This place, known today by its Turkish name, Göbekli Tepe, may very well be the oldest monumental structure ever created by human hands. It predates agriculture and yet suggests a level of social organization that challenges what we thought possible for hunter-gatherer societies. And the mysteries only deepen. Why would people who had not yet settled into permanent villages build such a massive and symbolic structure? Was it a temple, a ceremonial site, a gathering place for scattered tribes? And perhaps the more haunting question, why did they eventually abandon it? Over time, Göbekli Tepe was deliberately buried beneath tons of earth. Whether this was an act of reverence or something else entirely, we still do not know. What we do know is this. For thousands of years, people walked past this hill, unaware of the story it held. It raises a disturbing possibility. What else have we forgotten? What other pieces of our history lie hidden beneath soil and stone, mistaken for simple hills, or ignored as meaningless rubble? Göbekli Tepe reminds us that the past is not fixed. It is layered, elusive, and sometimes breathtaking. It tells us that human history is not a straight line from primitive to advanced, but a broken, spiraling path filled with lost knowledge and unsolved puzzles. And if something as significant as this could remain buried for 10,000 years, what else is waiting to be found? In the heart of Antarctica, where the ice stretches endlessly and time seems frozen, a single black rock stood out like a shadow on a field of pure white. It had rested there for tens of thousands of years, untouched by anything but wind and snow. But in the early 1980s, a scientist named Roberta Score, working with NASA's Johnson Space Center, spotted the rock during a meteorite search in the Allen Hills region. To the untrained eye, it looked ordinary, but it would soon become one of the most controversial stones in the history of science. The rock was officially named Allen Hills 84001, or ALH 84001. Back in the laboratory, its mineral composition and trapped gases told a remarkable story. It had come from Mars. Millions of years ago, a massive impact on the Martian surface had launched it into space. After drifting through the solar system for eons, it eventually fell to Earth, landing softly upon the Antarctic ice. But what made this meteorite extraordinary was not its journey. It was what scientists believed they found inside it. In the mid-1990s, a team of researchers led by physicist David S. McKay announced a discovery that made headlines around the world. Using electron microscopy, they claimed to have found microscopic structures inside ALH 84001 that resembled fossilized bacteria. These tiny, chain-like shapes looked similar to certain microbes found on Earth. If confirmed, it would mean that life, at least simple life, had once existed on Mars. Even the President of the United States gave a public address about the findings. The reaction from the scientific community was immediate and intense. Some hailed it as the most important discovery in the search for extraterrestrial life. Others urged caution. Could these structures have been created by non-biological processes? Critics pointed out that Martian chemistry may behave differently than Earth's, and that similar formations could arise from purely chemical reactions. Within months, multiple alternative explanations were published. The excitement gave way to doubt, and the debate began. As the years passed, the claim of fossilized Martian life became less accepted. No single piece of evidence was conclusive. No repeatable test could prove that the structures were once alive. ALH 84001 became a symbol, not of triumph, but of the limits of our understanding. It reminded scientists of a hard truth. To identify life, we must first define it. And even on Earth, that is not always easy. More than 200 definitions of life exist in the scientific literature. None are universally accepted. But even amid the controversy, ALH 8401 had changed something fundamental. It shifted the way we think about life beyond Earth. For the first time, we were not just imagining aliens, we were holding a piece of another world in our hands and asking if it once stirred with life. It opened a doorway to deeper questions. How would we recognize alien life if we saw it? Could something be alive by a standard we have not yet considered? The meteorite became more than a rock. It became a mirror, reflecting both the power and the limits of human curiosity. What exactly is life? It is a question that seems simple at first glance. We know it when we see it. A tree growing in sunlight, an insect crawling on a leaf, a human being breathing and thinking. But when scientists attempt to define life with precision, the simplicity begins to vanish. Across the disciplines of biology, chemistry, and physics, over 200 different definitions of life have been proposed, and not one of them satisfies everyone. In many ways, the question of what life is remains as elusive as the search for life itself. To navigate this complexity, scientists often rely on a general framework, 3 fundamental traits that all known life seems to share. First, life must have the ability to store information. This information might include instructions for building structures, controlling internal processes, or responding to the environment. Second, life must be able to catalyze chemical reactions. These reactions allow an organism to interact with its surroundings, gather energy, and perform vital functions. And third, life must be able to make copies of itself, self-replication. These 3 characteristics, information storage, catalysis, and replication, are not just theoretical. They are observable in all living systems on Earth. In our own biology, information is stored in deoxyribonucleic acid, or DNA. That information is read and translated by ribonucleic acid, or RNA. Proteins, constructed from amino acids, perform the majority of catalytic functions, from digesting food to building muscles. The loop closes when proteins, directed by RNA, create new strands of DNA. This cycle of chemistry allows life to persist and evolve. But there is a deeper level to this definition, one that bridges biology with physics. In the 1940s, the physicist Erwin Schrödinger proposed that life is a system that stores and transmits information in a way that allows it to defy the natural drift toward disorder. He framed life as a physical process, something that fights entropy by passing on ordered structures from generation to generation. This concept would later become central to molecular biology and lay the groundwork for our understanding of evolution. Evolution, particularly Darwinian evolution, offers yet another lens through which to define life. According to this view, life is whatever can undergo natural selection. If something can reproduce, and its offspring can vary, and some of those variations lead to greater survival or success, then evolution can take place. Over time, those beneficial traits accumulate. This process requires a way to store information, a mechanism to replicate it, and enough complexity for variation to arise. Evolution, in this sense, becomes the engine that drives all life forward. This definition, grounded in information, chemistry, and evolution, gives us a powerful tool, but it also sets boundaries. It tells us what life must be, at least in the forms we currently understand. Yet it also leaves space for possibility. Could there be systems that store information in a medium other than DNA? Could life arise without proteins or nucleic acids? Could there be entirely different chemistries that fulfill the same roles, yet look nothing like what we have seen? To define life is not only to understand ourselves, it is to open the door to everything we have yet to discover. If life is defined by information, chemistry, and replication, then what do we make of viruses? These microscopic entities can store genetic material, and they certainly reproduce, but only inside the cells of other organisms. A virus cannot build structures or catalyze reactions on its own. It lacks metabolism. It cannot move or respond to stimuli independently. And yet, it evolves, it adapts, it mutates. Some scientists consider viruses alive, others do not. They occupy a strange gray zone, neither fully living nor entirely inert. This ambiguity is not limited to viruses. It also applies to the very origins of life on Earth. Long before complex cells emerged, long before DNA and proteins ruled the molecular stage, life may have existed in a far simpler form. One popular hypothesis suggests that early life was built entirely around RNA, ribonucleic acid. RNA is unique. It can both store information and catalyze certain chemical reactions. In a world without proteins or DNA, RNA might have played all the necessary roles for life to begin, imperfect, fragile, and fleeting, but alive in a primitive way. This hypothetical RNA world would have been alien to us. No cells, no metabolism as we know it. Just strands of molecules drifting through warm, ancient oceans, occasionally replicating themselves if the chemistry was just right. It is hard to say when, exactly, the boundary between non-life and life was crossed. Perhaps it was not a sudden leap, but a gradual slide. A set of reactions became more ordered. Molecules became more cooperative. Eventually, something crossed the invisible line, from chemistry to biology. Amid all these uncertainties, there is one constant: water. Every known form of life depends on it. Life on Earth does not just prefer water, it requires it. Water acts as a stable solvent, allowing molecules to float, collide, and react without being destroyed. It can dissolve waste, carry nutrients, and regulate temperature. It helps form membranes, the protective boundaries that separate life from the outside world. Its unique properties make it the perfect medium for life's chemistry, and perhaps the only one suited for biology as we understand it. Could life exist without water? Perhaps. Scientists have speculated about alternative solvents, methane, ammonia, or even supercritical carbon dioxide. But water remains the most likely candidate, not because of our familiarity with it, but because of its chemical advantages. It is abundant in the universe. It is stable across a wide range of temperatures. It supports the complex interplay of reactions needed to sustain a living system. In the search for life beyond Earth, the first question we often ask is simple: is there liquid water? When we look to the stars in search of life, We often imagine distant, Earth-like planets orbiting alien suns. But perhaps we do not need to look so far. Hidden within our own solar system may lie some of the best candidates for extraterrestrial life, worlds that seem frozen, quiet, and desolate, yet hold beneath their surfaces oceans deeper than any found on Earth. These are not planets, but moons, and some of them, despite their outward appearance, may offer all the right conditions for life to arise and endure. Take Europa, one of Jupiter's largest moons. Its surface is a smooth, unbroken sheet of ice, crisscrossed with dark scars and fractures. At first glance, it looks lifeless, a cold and distant world far from the warmth of the sun. But beneath that icy shell lies a global ocean of liquid water, kept warm not by sunlight, but by the tidal forces of Jupiter's immense gravity. This constant stretching and squeezing generates heat within Europa's core, enough to melt the ice and sustain a vast subsurface sea. Where there is liquid water, energy, and the right chemistry, there is potential for life. On Earth, deep beneath the oceans, entire ecosystems thrive around hydrothermal vents, places where heat and minerals pour from the crust into the dark sea. Sunlight never reaches them, yet life flourishes. If similar vents exist on the ocean floor of Europa, they could provide the same kind of nourishment to alien microbes. In such a scenario, life on Europa would not just be possible, it would be almost expected. Enceladus, a small moon of Saturn, offers another compelling case. It is only a few hundred kilometers across, yet it has captivated planetary scientists since the Cassini spacecraft revealed towering plumes of water vapor erupting from its southern pole. These geysers burst through cracks in the surface ice, releasing water, organic molecules, and heat into space. This is not a theory or speculation. It is direct evidence of a salty ocean beneath the ice, rich with complex chemistry and warmed by internal processes. Unlike Europa, Enceladus allows us to sample its subsurface ocean without even landing on its surface. The plumes act like natural probes, ejecting material from the depths into space. Future missions could fly through these plumes, collecting samples and analyzing them for signs of biological activity. Enceladus may be small, but it is powerful, a frozen world with a living heart, whispering secrets into the vacuum of space. If life exists there, it may already be sending us clues with every eruption. Then there is Titan, Saturn's largest moon, and one of the most surreal places in the solar system. Titan is cloaked in a thick orange atmosphere, composed mostly of nitrogen and methane. It is the only world beyond Earth known to have stable liquids on its surface. But these are not lakes of water. They are lakes and rivers of liquid methane and ethane, flowing slowly through icy valleys under a sky dimly lit by a distant sun. At -180 degrees Celsius, Titan is unimaginably cold, but it is not dead. Could life exist in such an environment? It would need to be very different from anything we know. It would not use water as a solvent, but methane. Its biochemistry would move slowly, its metabolism frozen in time. Yet some scientists believe that such exotic life forms are possible, perhaps even inevitable, if the right molecular structures can emerge. The question is not whether life must be like us. It is whether the universe allows life to be other than us. Titan may be the best place to test that question. Beyond these moons, the gas giants themselves pose a strange and fascinating possibility. Jupiter and Saturn are massive spheres of hydrogen and helium, with no solid surface to stand on. Yet deep within their atmospheres, pressures and temperatures reach levels that can support complex chemical reactions. Could life exist there, floating, feeding, drifting in the winds of alien skies? On Earth, some of the most resilient microorganisms live high in the atmosphere, surviving ultraviolet radiation and thin air. Perhaps something similar could evolve in the gas giants, life that never touches the ground. Such creatures, if they exist, would be unlike anything we can imagine. They might be vast and balloon-like, buoyed by gases lighter than their surroundings. They could use chemical gradients to gain energy, sensing changes in pressure or magnetic fields. They would not walk or swim. They would drift, forever unanchored, forever suspended in a sea of storms. It is a thought both eerie and poetic. Life that lives in the clouds, never knowing the feel of solid ground, never needing it. These places, Europa, Enceladus, Titan, the atmospheres of the gas giants, remind us that life may not be rare, only overlooked. It may not require sunshine, blue skies, or even liquid water. It may emerge wherever conditions allow complexity to take root. And our solar system, quiet and familiar though it seems, may already be teeming with hidden life. We simply have not learned how to listen. In the cold, the dark, and the strange, life may be waiting, unfamiliar, unrecognizable, but very real. When we imagine life beyond Earth, we often picture something that resembles ourselves, carbon-based organisms with cells, water, and DNA. But what if life elsewhere does not follow the same rules? What if the universe allows life to take entirely different forms, built not from carbon, but from elements we rarely associate with biology? The more we learn about chemistry and physics, the more we realize that life, in principle, does not need to mirror Earth to exist. It may be stranger than we dare to believe. One of the most discussed alternatives to carbon-based life is silicon-based life. Silicon sits just below carbon on the periodic table and shares several of its bonding properties. Like carbon, it can form long chains and complex molecular structures. Some scientists have speculated that under the right conditions, silicon might substitute for carbon in the basic building blocks of life. This would result in entirely different biochemical pathways, perhaps slower, less flexible, but still capable of supporting something we could call living. However, silicon has limitations. Its bonds are generally weaker and less stable than those of carbon, especially in the presence of oxygen. On Earth, silicon usually forms solid, rigid minerals like quartz and sand, hardly ideal for the dynamic chemistry that life requires. But on a planet with low oxygen and high temperatures, silicon chemistry might become more viable. Life there could be crystalline rather than soft, heat-tolerant rather than water-dependent, and built on frameworks that resemble stone more than flesh. The idea of silicon life stretches our understanding, but it still belongs within the realm of chemistry. Beyond chemistry, some physicists have proposed life forms rooted in quantum systems. These would not be composed of molecules at all, but of quantum states, entangled particles that store and process information in ways radically different from DNA. In theory, such life could emerge in environments where quantum effects dominate, such as in the early universe, near black holes, or inside ultra-cold interstellar clouds. Life based on quantum information would not resemble anything biological. It would have no metabolism, no physical body, and no need for a traditional environment. Its existence would be defined by probabilities and energy transitions. If such beings exist, their thoughts, if they could be called thoughts, might be flashes of coherence in a sea of noise. They might perceive time differently. They might be unaware of us entirely, or they may already have passed through the universe, leaving no trace but patterns we have not yet learned to recognize. Even more exotic is the idea that life might emerge from plasma, high-energy, ionized gas that exists in stars, lightning, and interstellar space. In 2007, Russian physicist Vadim Sitovich conducted simulations showing that tiny dust grains suspended in plasma can spontaneously form self-organizing structures. These formations interacted with their surroundings, maintained boundaries, and showed signs of memory, basic traits that resemble the behaviors of living systems. While not alive in the traditional sense, they raise intriguing questions. Could complex plasma systems eventually evolve into something that fits our broader definition of life? Could they store information in their electric fields, replicate by splitting into stable daughter structures, and react to external stimuli with internal changes? If so, then stars, nebulae, or the upper atmospheres of gas giants might not just be fields of radiation and light, but cradles for a kind of life born not from chemistry, but from energy, motion, and self-organization. This vision of plasma-based or quantum-based life pushes the boundaries of what we call biology. It challenges us to think beyond cells and molecules, to imagine existence not as a property of matter, but of behavior, of interaction, structure, and evolution. In such a framework, life is not tied to any specific element or temperature range. It is the emergence of complexity that maintains itself and adapts to its environment, no matter what form that complexity may take. If these forms of life exist, they may be all around us, or they may have existed in the distant past, born in the chaos of the early cosmos and extinguished long before galaxies took shape. Their lifespans may be measured not in years, but in quantum fluctuations. They may encode information in dark matter or whisper in gravitational waves. And yet, to us, they would remain invisible, forever outside our instruments, forever beyond our grasp. But that is the beauty of the unknown. We do not need certainty to imagine. We do not need proof to ask bold questions. As we continue to search for life beyond Earth, let us not be bound by familiar forms. Let us be ready to find life that breathes fire instead of air, that swims in magnetic fields rather than oceans, that thinks in pulses of light instead of neurons. The universe may be more alive and more mysterious than we have ever dreamed. In the early 1950s, the question of how life began remained firmly in the realm of speculation. Philosophers, theologians, and scientists alike could only guess at what mysterious process had sparked the first living things. But that changed in the year 1952, when a graduate student named Stanley Miller, under the guidance of Nobel Prize-winning chemist Harold Urey, attempted to recreate the conditions of the early Earth inside a glass laboratory flask. Their goal was simple, yet revolutionary: to see if the building blocks of life could arise from chemistry alone. Miller filled a closed system with water to represent the ancient oceans, and added a mixture of gases thought to be present in Earth's primordial atmosphere: methane, ammonia, and hydrogen. Then, he introduced an electric spark, mimicking lightning storms that would have been common on the young planet. For the first day, nothing seemed to happen. But by the end of the week, the water had turned a deep red. Something extraordinary was taking place. When Miller analyzed the liquid, he discovered that it now contained amino acids, the fundamental components of proteins, and by extension, of life itself. This experiment sent shockwaves through the scientific community. It demonstrated, for the first time, that organic molecules essential to life could be synthesized from simple inorganic compounds under plausible prebiotic conditions. The spark did not create life, but it showed that nature could produce the ingredients of life without any guidance. The atoms involved, carbon, hydrogen, oxygen, and nitrogen, are among the most common elements in the universe. And yet, when arranged the right way, they hold the potential to become something more. Miller's work laid the foundation for the modern study of abiogenesis, the origin of life from non-living matter. Further analysis of his sealed samples, decades later, revealed even more amino acids than he had originally detected, including some not used by life today. This suggested that the early Earth may have had a rich and diverse chemical landscape filled with possibilities. While the exact path from those first amino acids to fully functioning cells remains uncertain, the Miller-Urey experiment proved that the spark of life need not come from the divine. It may simply be the inevitable result of chemistry and time. Life as we know it depends on complex organic molecules, particularly amino acids, the building blocks of proteins. On Earth, these molecules can form in the right chemical environment, as the Miller-Urey experiment demonstrated. But what if they did not originate here at all? What if the seeds of life came from beyond our planet, delivered across the vastness of space? For decades, scientists have turned their attention to the ancient messengers that fall from the sky, meteorites. And within these rocks, they have found something extraordinary. Some meteorites contain amino acids, real, verifiable organic molecules, formed not on Earth, but in the cold vacuum of interplanetary space. These findings suggest that the chemistry of life is not unique to our world. In fact, it may be common throughout the solar system. One of the most compelling examples came from a tiny asteroid named Ryugu. In the year 2014, the Japanese space agency launched the Hayabusa 2 mission, a spacecraft designed to visit Ryugu, collect material directly from its surface, and return that sample to Earth. After a journey lasting several years, Hayabusa 2 successfully gathered grains of Ryugu's surface and brought them home in late 2020. When scientists analyzed the sample, they were astonished. It contained dozens of organic compounds, including several amino acids. These were not contaminants from Earth. They were formed on the asteroid itself, shaped by slow chemical reactions over billions of years, possibly triggered by solar radiation or the heat from short-lived radioactive elements trapped in the rock. What makes this discovery so powerful is not just the presence of amino acids, but their diversity. Among the molecules identified were both types familiar to Earth's biology and others that life here does not use. This suggests that Earth's biochemistry is not the only option. Out there in the cosmos, other configurations may be possible. The prebiotic chemistry of Ryugu may have been one of countless miniature laboratories scattered across the solar system, each experimenting with molecular arrangements long before the Earth had even cooled. But these organic molecules are not limited to meteorites and asteroids. In recent years, astronomers have detected them drifting between the stars. Using powerful radio telescopes, scientists have identified glycine, the simplest amino acid, in dense molecular clouds. These clouds are the birthplaces of stars and planets. In them, dust and gas gather, collapse, and ignite into suns. And within those same clouds, nature is already performing chemistry, building the ingredients of life before any planet has even formed. Some of the most distant and energetic objects in the universe, quasars, located in galaxies billions of light years away, also show traces of complex organic compounds in the light they emit or absorb. This indicates that the essential chemistry of life was already present in the young universe, only a few billion years after the Big Bang. Life may not be a rare accident, but a natural outcome of cosmic evolution. The universe is not just a container for life. It may be, in some sense, a maker of life. These findings invite us to view the cosmos differently, not as a cold, indifferent void, but as an immense, ancient workshop. Across dust clouds and icy rocks, in the cores of asteroids and the tails of comets, the universe has been mixing and assembling organic ingredients for eons. Our own planet may have received these molecular gifts in its earliest days, carried by waves of celestial debris. Each meteorite that falls to Earth might be more than just a rock. It might be a fragment of a recipe written in the language of the stars. For life to emerge, the conditions must be just right, not too hot, not too cold, not too dry or chaotic. Astronomers call this delicate balance the habitable zone, a region around a star where temperatures allow liquid water to exist on a planet's surface. It is often called the Goldilocks zone because everything must be neither too much nor too little. A planet too close to its star will boil its oceans into steam. A planet too far will freeze solid. But in that narrow band of possibility, life as we know it can flourish. Our own Earth sits squarely in the Sun's habitable zone. It receives just enough energy to sustain liquid water, but not so much that it becomes uninhabitable. Venus, though similar in size to Earth, orbits slightly closer to the Sun. That small difference has made all the difference. Venus once may have had oceans, but over time, a runaway greenhouse effect turned it into a furnace, with a surface hot enough to melt lead. Mars, on the other hand, lies near the outer edge of the zone, colder, drier, and now barren. But even being in the habitable zone is not enough. A planet must have a stable atmosphere, the right chemical ingredients, and protection from cosmic radiation. It must also have a source of internal energy, volcanoes, magnetic fields, tectonic activity, to help drive complex chemistry. These conditions depend on more than a planet's distance from its star. They depend on what that planet is made of. And that brings us to another layer of the story, the origin of the elements themselves. The basic ingredients for life, carbon, oxygen, nitrogen, phosphorus, and sulfur, were not present at the birth of the universe. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything else came later, forged in the hearts of stars through the process of nuclear fusion. When massive stars died in spectacular supernova explosions, they scattered these elements across space. New stars and planets formed from that enriched material. Life could not begin until the universe had cooked the proper recipe. This means that the first stars, though brilliant and enormous, could not have supported life. They lived fast and died young, enriching the cosmos with each cycle. Only after several generations of stars did enough heavy elements accumulate to build rocky planets and liquid water. Life, as we know it, requires this cosmic recycling. It is not just chemistry, it is history. Each breath we take, every drop of water, every cell in our bodies, carries atoms that were once part of ancient stars. So, where can life begin? It begins in the quiet, stable regions around stars. It begins where water can flow and organic molecules can mix and react. It begins on worlds shaped by the debris of ancient supernovae, warmed by just the right amount of sunlight. In short, life begins where the universe has been patient, where time, chemistry, and starlight converge in a moment of perfect balance. And Earth, so far, is our only known example of that delicate alignment. Up to this point, our search for life has largely been grounded in what we know: water, carbon, gentle sunlight, and complex chemistry. But what if life is not limited to the familiar? What if the universe permits forms of life so strange, so profoundly different from our biology, that we might not even recognize them as alive? Some scientists have begun to ask this very question, not as an exercise in fantasy, but as a serious inquiry into the limits of physics, chemistry, and our own perception. Consider neutron stars, collapsed remnants of massive stars where gravity has crushed matter to extremes. In these places, atoms are stripped of their structure. Protons and electrons fuse into neutrons. The matter is dense beyond imagination, and the laws of physics behave in unfamiliar ways. Yet, in 1973, physicist Frank Drake proposed that within the superdense interior of a neutron star, patterns of nuclear particles could form complex, self-sustaining structures, capable of interaction, replication, and even evolution. This form of hypothetical life would not rely on molecules, cells, or DNA. Instead, it would be governed by the strong nuclear force, and it would operate at speeds and energy scales vastly different from ours. It would be born in violence, live in pressure, and die in collapse. To us, it would be invisible. But by a deeper definition, something capable of storing information, reacting to its environment, and evolving, it might still qualify as life. A life of pure physics, not of biology. Even more mysterious is the idea of life based on dark matter. The universe we observe, planets, stars, galaxies, is only a small fraction of what truly exists. Most of the cosmos is made of dark matter and dark energy, invisible to our instruments and poorly understood. But if dark matter interacts with itself through unknown forces, it could form stable structures, dark atoms, dark molecules, perhaps even dark biology. These entities could evolve completely outside the realm of ordinary matter. Such life, if it exists, would pass through our solar system unnoticed. It would not reflect light, it would not emit radiation we could detect, and it might be governed by rules of physics entirely unknown to us. Yet, it could be thinking, moving, changing, perhaps even ancient. It may have appeared long before the first stars formed, drawing its energy from forces we have not yet discovered. We call it dark not only because we cannot see it, but because it lies beyond the reach of our understanding. And then there is the earliest universe itself. In the first second after the Big Bang, temperatures and densities were unimaginably high. Particles collided with unimaginable force. In that brief chaos, unknown interactions may have created complex, fleeting arrangements, perhaps structures capable of evolution, replication, even consciousness. If such life arose, it would have been extinguished quickly as the universe expanded and cooled. No trace would remain. Yet for a moment, in the primal fire of creation, the universe itself may have been alive. One afternoon in the summer of 1950, the physicist Enrico Fermi was walking to lunch with colleagues at the Los Alamos laboratory. Their conversation drifted to the topic of extraterrestrial life, about the vastness of space and the probability of other civilizations. They laughed, they speculated, and then the conversation moved on. But Fermi was quiet. Suddenly, he stopped and asked a question that has haunted scientists ever since. Where is everybody? A simple question, built on a troubling logic. The reasoning is straightforward. The universe is vast beyond comprehension. Our galaxy alone holds hundreds of billions of stars, and many of those stars host planets. Some of those planets will lie in their star's habitable zone. Some will have liquid water. Some may even host life. And if life is not rare, then intelligent life should also emerge, at least occasionally. Over the course of billions of years, even one civilization could explore or colonize an entire galaxy. And yet, we see nothing. There are no radio signals drifting to Earth from distant stars, no alien spacecraft cruising through the solar system, no evidence of ancient ruins on the Moon or Mars, no atmospheric signatures of life on nearby exoplanets. Despite decades of searching, every effort to detect extraterrestrial intelligence has failed. We have pointed our telescopes at thousands of stars, listened to the sky in hundreds of frequencies, scanned for artificial structures, and found only silence. The cosmos remains stubbornly quiet. This unsettling contradiction is known as the Fermi Paradox. If intelligent life is common and the universe is old, then we should expect to see some evidence of its presence. But we do not. Either our assumptions are wrong, or we are missing something fundamental. Perhaps life is far rarer than we imagine. Perhaps the conditions that led to life on Earth are unique, or close to it. Perhaps the spark that ignites intelligence is far more difficult to achieve than we believe. Or perhaps civilizations do arise, but they do not last. The same intelligence that builds cities, computers, and starships may also build weapons, unstable governments, and unsustainable technologies. Civilizations might routinely destroy themselves before they reach the stars. Others may lose interest in exploration. Some may retreat inward, living in simulated realities or digital worlds. The silence we hear may be the echo of extinction, voices that once spoke, now long gone. There is also the possibility that life is common but unrecognizable, that alien civilizations use forms of communication we do not understand, that their biology is based on principles foreign to us, that they live in environments we cannot detect, or simply have no reason to make contact. Perhaps Earth is part of a vast cosmic preserve, observed but untouched. Or perhaps there is a filter, a hidden barrier that most civilizations never pass, a test that only a few survive. And maybe, just maybe, we have not reached it yet. The Fermi Paradox does not offer an answer. It asks a question. A quiet, disturbing question that lingers in the background of every scientific mission, every planetary probe, every SETI scan. If the universe is full of life, then why do we seem so alone? The silence is not proof of emptiness, but it forces us to confront the possibility that we might be early, that we might be rare, or that the universe is whispering in a language we have not yet learned to hear. Perhaps the simplest explanation for the silence is that life itself is rare. The emergence of biology may require such an improbable chain of events that Earth could be one of very few places where it ever occurred. Even if microbial life is somewhat common, intelligent life might be exceedingly rare. Evolution is not a ladder. It does not aim toward consciousness. Intelligence may be a fluke, a brief, unstable spark that burns out quickly, leaving behind only fossils and dust. Another possibility is that life exists, perhaps even in abundance, but we do not know how to recognize it. It may communicate through means that we cannot detect, through gravitational fields, quantum entanglement, or structures we mistake for natural phenomena. It may not wish to be found. Some have suggested that Earth is inside a kind of galactic wilderness preserve, watched but never disturbed. To us, it feels like silence, but from their perspective, it may be respect or even mercy. And then there is the vastness of space itself. The distances between stars are so great and the timescales so immense that contact may simply be impractical. Civilizations may flicker into being and vanish before their signals ever reach one another. Communication might be possible, but unbearably slow. The universe does not guarantee connection. It only allows for the possibility. And so we wait, surrounded by stars, wondering if someone else is waiting too. If we endure, if humanity survives its own missteps and limitations, we may one day scatter among the stars. Our probes may chart new worlds. Our descendants may walk on distant moons. The Milky Way could become a canvas for our curiosity and ambition. But even if we spread across the galaxy, our time will still be brief compared to the life of the cosmos. Civilizations may rise like fireflies in the dark, bright for a moment, then gone. We may become one of them, and in the silence, we may find remnants. Perhaps someday we will uncover what others left behind. Ruins beneath alien skies, machines drifting in interstellar space, signals carved into the background radiation. Their creators long vanished, but their questions echo still. Who were they? What did they seek? Why did they disappear? If we persist long enough, We may not be the first to explore the galaxy, but we may be the first to remember it. And in those discoveries, we will not just be searching for others. We will be searching for ourselves. Long ago, Göbekli Tepe lay buried beneath centuries of silence. To the eye, it was only a hill, ordinary, forgotten. But beneath the dust was a monument, a message, a memory from a world that no longer exists. Perhaps the universe is filled with such monuments, not built from stone, but from starlight and gravity, from molecules and information. Perhaps we have already passed them in the night sky, unaware of what they are. Perhaps they are waiting, silent, patient, hidden among the stars. To search for life beyond Earth is not only to look outward, but inward. It is to ask what it means to be alive, to wonder how rare consciousness truly is, and to face the possibility that we are early or alone. Yet even in the silence, the search is not in vain. It is the most human of pursuits, a reaching beyond ourselves, a longing to connect. Somewhere, out there, may rest another Göbekli Tepe, not of stone, but of signal, not buried in earth, but in space, waiting not to be believed, only to be found. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.